Okay, so next we are going to get a quick overview of machine learning on structured data, basically the data models that we study in this course. And I'm going to start with general machine learning, regardless of this course. The basic ideas, again, I'm assuming that students who take this course have taken a basic course on machine learning, so we have the background. Uh, you know the theory. I'm just basically verifying that we are on the same page and then aligning our terminology. Okay, so the core task in machine learning is basically as follows. We have a space X of examples or instances. We have a space of outputs, the target space Y, and there's a function, unknown function F from X to Y. Now we really want this F. We want to know what it is. We want to be able to mimic it or put our hands on F, but we don't have it. We do get a set of examples, S. Okay, these are examples xi, yi, xi in x, yi in y, telling us how f is behaving. So yi, we think of it as f of xy. Okay, so we also have a space of hypothesis. This is a bold H. Okay, this is the candidate functions that we can choose. It doesn't necessarily include f, but what we want is to find a h that is as close as possible to f. Okay, h that is closest to f. Okay, and for that to make sense, we assume that S is somehow representative of the space of examples. Okay, so S is chosen randomly, say independent and identically distributed choice of examples. Okay, so the common types of machine learning tasks or settings, they differ based on this set Y. So in binary classification, it is 0, 1, or true, false, yes, no. Multi-class classification generalizes it into K outputs, K classes. Multi-label means that we can associate with each X multiple labels, multiple classes. Okay. Regression means that we basically want to find or to learn a numeric function, height, weight, level of satisfaction, number of purchases, and so on. And multivariate means that we want to predict multiple numbers at the same time, height and weight at the same time, for example. Okay. Now, they are related. For example, a binary classification is typically learned by learning a regression model, H prime, which is, think of it as a probability or a score function on how likely X is to be classified as 1. Okay, and then you have a threshold, and you say, well, if the score of X is less than the threshold, then let this final decision be 0, otherwise it is 1. Okay, we'll revisit that later. And there's also the multivariate version, okay, multivariate regression that corresponds to multi-class classification. We'll also see that later. Okay, now training is the actual process of computing this best H given the examples S. How do we do that? Well, we typically do it by defining a loss function. Loss of S given a candidate H. Okay, loss will tell us how far off H is from, behaving as we would expect it on S. So basically, this is a function that processes the triples xi, the real yi, and what H is saying about xi, and comparing the yi to the xi. And so what we're looking for is H that minimizes the loss. Okay, so the loss can be, for example, go over all of the examples and for each one take a difference between the real yi and what H predicts. And if this is in some norm space or a metric space, um, you get a number. Okay, you get some measure on how far H is from S. Okay, now an important class is that of the parametric models, which are basically hypothesis spaces where all the functions have the same structure, but they differ in the parameters. They have the same set of parameters, theta 1 to theta q, but each H assigns different numbers, different weights to these parameters, theta 1 to theta q. These parameters again called weights. They, sometimes you can call them coefficients, same number of parameters for every model. And so the goal is to basically compute the best theta. Okay. And there are also other parameters, other models that are not necessarily parametric, like decision trees. They differ in their structure, and different hypotheses can have different number of parameters. And KNN, that's another example of a K nearest neighbor, another example of a non-parametric model. So it's not all about parametric, but these are definitely important in general and important for the course. Okay, now regularization is basically a way of biasing the learning to models that we prefer. Why do we prefer? Because we believe that they generalize better, beyond the training. So regularization penalizes H typically for being complex. And the rationale is that if your function is too complex, then it might overfit, it might hang on to the nuances of the examples. And if you force it to be simple, then you also force it to grasp that the big picture that is uh, basically expressed or shown in the examples of S, and thus better generalize. Okay, let's see some common loss functions. So a loss function will typically look like error of S on the model H theta, and plus the regularization that takes only H theta as an input and gives us a measure of regularization times some lambda. Lambda is a way that tunes, how much regularization we want to have. Here in the examples, I'm using yi hat as hxi as opposed to yi. And we want yi hat and yi to be close. So the examples of error functions, we have mean square error, where we basically sum up the differences between yi and yi hat, the prediction and the label squared. Mean absolute error, we sum up the absolute values. Okay, Huber loss is a combination of them, where on small values we use mean square, and on large values we use mean absolute error. Okay, there is cross entropy that basically applies to binary and multi-class classification, where basically what we learn is actually this YIC. What is we get a score, we learn a score of how likely it is that XI should be mapped to the class C. So this is YIC hat. And the real YIC is 1 if YI is labeled C, and 0 if YI C is if XI is labeled to something else. Okay, so assuming that this number is always positive, what we get is basically something that measures how different our prediction is from the original labeling using the KL divergence. Okay, examples of regularizations: there is a lasso regression where we basically penalize for weights that are too large. So we simply sum up the weights taken in absolute values. Okay. And radial correction where we take the squares of the weights. Okay, same idea. So basically, what happens here is that once we have the loss function over a parametric model, we translate our machine learning problem into an algorithmic optimization problem. Okay? And there are some traditional algorithms or machine learning setups where you solve this problem exactly, like support vector machines. But as the models become more complex, more parameterized, you have more higher volumes of training data and so on, it is not practical to think of the actual optimum for your function or for your optimization problem. And in fact, you do not necessarily want to solve this optimization problem exactly to avoid overfitting. So next, we will see what you actually do in practice.